Welcome to lecture number 9 for ECE 463 Modern Control, Dynamics of a Two-Link Arm. Now where we want to get to at the end of this lecture is to be able to simulate a two-link arm as follows. This is kind of like your shoulder and elbow. I've got a 1 kilogram mass attached to a rod that's 1 meter long, attached to a second 1 kilogram mass that's 1 meter long. If I let it go under free fall, it'll follow some path like this. And this is a kind of nasty nonlinear system. It's actually a chaotic system. How do you find the dynamics of a two-link arm so that I can simulate its behavior like this? That's kind of what this lecture is all about. Come up with those dynamics. And to do that, we'll use Lagrangians. Now, in this lecture, we're going to look at coming up with the dynamics for a robotic arm. Typical industrial robots have 3 degrees of freedom. That has the base, so you can sit there and turn around. The shoulder goes up and down, and the elbow. That lets you reach any place in 3 space. In addition, the wrist typically has another 3 degrees of freedom, so you can sit there and rotate the wrist, twist up and down. I think there's a third one, the gripper. That way I can reach any place in 3 space and have the tip of the robot arm always orthogonal to the thing you're trying to pick up or put down. Now, a 3 degree of freedom robot, or even a 6 degree of freedom robot, has dynamics that work out to about a 6-page derivation. So we're not going to do that. Instead, what we're going to look at is a 2 degree freedom robot. And think of that, if I take the robot, turn the base towards whatever it is I want to pick up, and lock the base. I now have 2 degrees of freedom, the shoulder and the elbow, to reach out to the part. In addition, I've got the wrist. The wrist can sit there and move around and figure out what I have to do to basically be perpendicular to it, pick up the object. We'll ignore the wrist. I just want to get the 2 degrees of freedom, the shoulder and the elbow, to reach any point in 3 space, or 2 space. So, the dynamics that we'll be defining are as follows. I've got 2 links. Each one is 1 meter long. I've got the first link, that's the shoulder. It can turn by theta 1. That's the theta relative to the vertical. The second one, the link, is relative to the first link. Again, the Q2 isn't actually relative to the x-axis, it's relative to the previous link. Kind of figure if I lock my elbow and turn my shoulder, the elbow hasn't moved. The motor attached to the motor hasn't moved, or the motor attached to the elbow hasn't moved. But the angle relative to Earth reference frame changes with the first link. If, on the other hand, I move the second link relative to the first link, that's the motor turning, that's your Q2. So typically in robotics, every link is relative to the previous link. So Q2 is the angle of L2 relative to the angle of Q1. And what I care about is the tip force, or the tip position. I want to figure out where's the tip of the robot, and that's what I want to control. And the reason I want to do that is if I'm painting, I want to have the tip move along a certain point or a certain surface. If this is a robotic pick-and-place machine, I want to pick up a component, place it on a circuit board. There's a very specific XY coordinate I want to put the tip at. So how do I do that? Well, the first thing we need to come up with are the dynamics of the robot. So to come up with the dynamics, again, we'll use the Lagrangian. I've got 2 masses. I'm assuming this is a lump mass model. All the mass is at the elbow, and all the second mass is at the wrist. Each one's 1 kilogram, and each link is 1 meter. To find the kinetic energy, potential energy, I need to find where's the position of mass 1 and where's the position of mass 2. So mass 1, with the reference frame or coordinates I've defined here, the xy coordinate, x is cosine theta 1, y is sine theta 1. Taking the derivative, x1 dot is the derivative of cosine theta 1 minus sine theta 1 dot. The derivative of y1 is cosine theta 1 dot. Again, you've got the partial with respect to theta 1 times the partial theta 1 with respect to t gives you the second term, theta 1 dot. Mass 2. This gets a little more complicated. The position of mass 2 is the position of mass 1 plus the cosine of the net angle. The net angle is theta 1 plus theta 2. Taking the derivative, x2 dot is, same as before, minus sine theta 1 dot plus Derivative of cosine is minus sine times derivative of the inside, theta 1 dot plus theta 2 dot. The y-coordinate, y2, is y1 plus cosine theta 1 plus theta 2. No, correction, sine theta 1 plus theta 2. Taking the derivative of y1 is the same as before, cosine theta 1 dot, plus the derivative of sine is cosine theta 1 plus theta 2 times theta 1 dot plus theta 2 dot. Now in robotics, this gets a little bit unwieldy, all these sines and cosines, so the notation typically used in robotics is C1 means cosine theta 1, S1 means sine theta 1, and save some writing. And if I have a 1, 2, that means sine of theta 1 plus theta 2. So these same equations would just be x1 is cosine theta 1, y1 is sine theta 1, x1 dot is minus sine theta 1 dot, y1 dot is cosine theta 1 dot, and so on. Now let's form the kinetic energy and potential energy. For the first mass, kinetic energy is 1/2 mv squared. Substituting, x1 dot is minus sine theta 1 dot, y1 dot is cosine theta 1 dot. Squaring gives me sine squared plus cosine squared, gives me 1. So the kinetic energy is just 1/2 theta 1 dot squared. Potential energy is mgx, because I have x pointing up, gravity's pointing down. So they'll just be g cosine theta 1. That's for mass 1. Now let's go to mass 2. Kinetic energy is 1/2 mv squared. Substituting for x2 dot squared, I get this for x2 dot. Here's y2 dot. Squaring them, I got sine squared, second term squared, and the cross term, well, here's the cosine squared, second term squared, and the cross terms. 2 sine theta 1 plus theta 2 times a half, 2 times a half cancels. So here's the cross term. And over here I get the cross term again. Times 2 divided by half gives you this. Simplifying, sine squared plus cosine squared is 1. Sine squared plus cosine squared is 1. And these two terms come together. Now what isn't real obvious, but from trigonometry, sine A sine B plus cosine A cosine B is cosine A minus cosine B. So these guys right here simplify. That's your cosine cosine, sine sine. Simplify to just cosine theta 2, theta 1 dot plus theta 2 dot. So grouping terms together, the kinetic energy is just 1 plus cosine theta 2, theta 1 dot squared. So here's the theta 1 dot squared, there's the theta 1 dot squared. Here's another theta 1 dot squared, so half times plus a half gives you 1, plus cosine theta 2, plus 1/2 theta 2 dot squared, and the cross terms. Theta 1 dot times theta 2 dot times 2 times a half gives you 1, plus cosine theta 2, theta 1 dot, theta 2 dot. So there's the kinetic energy, and the potential energy is g C1 plus C12, the first mass and the second mass. Putting that all together, the Lagrangian is as follows. So the Lagrangian is the kinetic energy minus potential energy. Here's the kinetic energy. Here's the potential energy. Simplifying, you get this mess for the Lagrangian. That's step 3. Now step 4 is start taking the partial derivatives. The torque on the first link, that's the shoulder, is the full derivative with respect to time of the partial bell with respect to theta dot minus the partial bell with respect to theta 1. The torque on the second joint, the elbow, is the full derivative with respect to time of the partial bell with respect to theta 2 dot minus the partial bell with respect to theta 2. So let's do that now. Starting with theta 1, here's my Lagrangian. Take the partial with respect to theta 1 dot, and here's the theta 1 dot right here. gives you 2 times 1.5 plus cosine theta 2, theta 1 dot. Nothing. Here's the theta 1 dot. 1 plus cosine theta 2 dot. And that's it for theta 1 dots. Minus the partial with respect to theta 1. Again, there's nothing here, nothing here, nothing here. There's a theta 1. Derivative of cosine is minus sine. Minus 2g sine theta 1. Minus g sine theta 1 plus theta 2. Now take the full derivative, and here you do the chain rule. Derivative of the second term is theta 1 double prime. Derivative of the first part gives you 2 sine theta 2 dot, theta 1 dot with a minus sign. Over here, derivative with respect to the second term is theta 2 double prime. Derivative with respect to the first term gives you minus sine theta 2 dot times theta 2 dot. Gives you theta 2 dot squared. Plus the gravity terms. Okay, so there's the first term. That's the first set of dynamics. The second term is now take the partial with respect to theta 2. That'll give you the torque on the second link. That's the full derivative with respect to time of the partial with respect to theta 2 dot minus the partial with respect to theta 2. Partial with respect to theta 2 dot. Again, looking through here, here's a theta 2 dot. Gives you theta 2 dot. Here's another theta 2 dot. 1 plus cosine theta 2 theta 1 dot. And that's everyone. Minus the partial with respect to theta 2. And here's the theta 2. Gives you minus sine theta 2 theta 1 dot squared. There's one. Minus sine theta 2 theta 1 dot theta 2 dot. And here's a term. Minus a minus g sine theta 2. Let's see. Now take the full derivative with respect to time. It gives you theta 2 double prime. Chain rule. Derivative with respect to the second term gives you theta 1 double prime. Derivative with respect to the first term gives you minus sine theta 2 dot theta 1 dot. And clearing out the signs. So here's the equation for the torque on the second link. So, and the net result are these two terms. Now, typically in robotics, I rewrite this as follows. I'll take all the accelerations, put them together, times something. This is the mass matrix. That's equal to the torque. Bring all the other terms to the other side. I'll have all these square terms. Those are the Coriolis forces and gravity forces. Now, the Coriolis forces correspond to, like an ice skater, when the ice skater goes into a spin and brings her arms in, energy has to stay constant. If my rotational inertia drops, then the speed has to increase so that the rotational energy remains constant. That's the Coriolis force. As you change your inertia, I get acceleration terms. That's what these are. I've got the mass matrix. If the mass matrix ever goes to 0, like if you have an ice skater and you point your arm straight up, I become a line, in theory, which would have 0 rotational inertia. If the mass or inertia ever goes to 0, the acceleration goes to infinity. Again, energy has to stay constant. And I have these gravity terms. Basically, a robotic arm is highly nonlinear. With that, I can now simulate it. If I know the angles and velocities, I can calculate acceleration. If I know the acceleration, I can integrate once, get velocity, integrate twice, I get position, and iterate every 10 milliseconds. That'll be the dynamics of the robot. And a simulation that does that is as follows. This is the code to link dynamics. I'm going to pass to it the angle, angular velocity, and joint torques. It'll go through this equation, calculate the acceleration, and return the acceleration. And these equations right here, there's the mass matrix, the Coriolis force matrix, and gravity matrix. The acceleration then is just the inverse of the mass matrix times torque plus Coriolis forces plus gravity forces. I can then simulate it. In free fall, I just let the torque be 0, calculate the acceleration, integrate to get velocity, integrate to get position. And this is what it looks like. This is a 2-link arm in free fall. Kind of swings back and forth. Some of this isn't real obvious, but that's just the way it behaves. I've got kinetic energy, potential energy bouncing back and forth. The total energy should stay constant. Again, I don't have any inputs, so there's no place for the energy to go. Basically, the energy is bouncing back and forth. Sometimes it goes to the first link, sometimes it goes to the second link, sometimes it's potential energy, sometimes it's kinetic energy. But it should add up to a constant. Let's get these kind of strange whipping motions like that. That's just how it behaves. This is when the torque is 0. If I add friction, like let's have the first link, the torque is minus the velocity, that's friction. If I add a whole bunch of friction, here's how it behaves. And it's kind of like it's swinging back and forth in molasses. It decays out. I can play games such as, suppose I put friction on the first link, put friction on the second link, but not the first link. So this link right here, the elbow, has friction, but the base doesn't. See, that's how it behaves. Right there where the second link is moving is dissipating energy. That's your friction. You can see that the height is decreasing, meaning it's losing energy. Or play other games. Let's add friction to the first link, but not the second link. So again, this first link has friction. The second link spins freely. So every time the first link moves, it's dissipating energy. Thing to note about this, these are rather nasty nonlinear dynamics. But using Lagrangians, I can calculate what those dynamics are. It's not a lot of fun. It's kind of tedious. It's kind of hard. But then this is a senior level course in electrical engineering. It's not supposed to be easy. The saving grace, however, is given a robot, I only have to calculate the dynamics once. Or in this class, once we calculate the dynamics, we'll leave the system alone and then try to control it. Thing to note, this is actually a chaotic system. If I give it an initial condition, it's going to be following a pretty obscure path. That's actually chaos. Now what chaos is, if I take the initial condition and perturb it just a little bit, eventually it'll follow a completely independent path. So minute disturbance, a minute change in the initial condition produces a large change over time. That is the butterfly effect. It's part of chaos theory. It's given a system, this like a 2-link robotic arm. It also applies to weather. If I change the initial condition just a hair, it'll have vastly different outcomes. What Edward Lorenz kind of called was the butterfly effect, saying that with weather, if you have just a little bitty change in the initial condition, say a butterfly flapping its wings, that butterfly will change the initial condition, change the trajectory the weather takes, so that without the butterfly, I wouldn't have a hurricane, but with the butterfly, I do have a hurricane. Hence, the flapping of a butterfly wing can cause a hurricane. That's the butterfly effect. Basically, it's a chaotic system, like the two-link robotic arm. Suppose I want to find the eigenvalues of this system. Now, eigenvalues only apply to linear systems. This is highly nonlinear, so I can't really say eigenvalues with it. But what I can do is pick an operating point and linearize about that operating point. If I linearize about 0, 0, which is the arm pointing straight up, then if I assume theta 1, theta 2 is roughly 0, velocity is roughly 0, all these higher order terms go to 0. Basically, if theta 1 is 0.01 times 0.01 times 0.01, becomes so small I can ignore it. All the higher order terms go away. Sine theta 1 becomes theta 1. Sine theta 1 plus theta 2 becomes theta 1 plus theta 2, and so on. Put all that together, and I wind up with theta 1 double prime is g theta 2. Theta 2 double prime is g theta 1 plus 3 theta 2. So here's your dynamics. In free-fall, the eigenvalues then would be minus 5 plus 5 minus 1.93 plus 1.93. So this is an unstable system. And if you give it a small initial condition, let it go, it falls. It's unstable. Oops, I think I still have friction on the first link. But anyway, it falls, it's unstable. If you let it run, then what happens is it'll go down to the bottom and the two links will swing back and forth. That's what the time response looks like. Basically, you've got two different frequencies in here, the two eigenvalues. So in summary, Lagrangians are able to determine the dynamics of a two-link robotic arm. The procedure is to find the kinetic energy, potential energy of each link. It's rather ugly, but not too bad. It's like a 2-page derivation. A 6-link robotic arm is about a 10-page derivation, so we'll leave that for a different course. Difficult, but at least for given a robotic arm, you only have to do it once. Note, as a sidelight, we spent considerable time in 761 robotics designing feedback controllers for this system. So for this class, we'll just kind of look at the dynamics, showing how you do Lagrangians with it. Much more detail on how to control robotics like this will be covered in 761 robotics. So that's lecture number 9, two-link robotic arm for ECE 463.